Okay, so for the tank, we got a inverted right circular cone. With a height of 6 and a radius of 3. So the radius of 3 is up here. Okay, and it's got hot chocolate, 1060 kilograms per meter cubed, and we want the work to get, it's all full, and we want the work to get it all out. Okay, so I want to, so there's two ways you can orient your axes, your frame of reference here, and there's trade-offs with each one. So we could put the origin here. And what's the good thing about that? Well, then the distance that every layer has to go is simply whatever coordinate that is. Okay, if you put your axis like this and then positive going down, then whatever distance your layer has to go is just simply that coordinate, like y. Okay. The other way to do this is to put your axis, you put your origin here, and the nice thing about that is then this your linear relationship between radius of the layer and this distance is a lot easier. It's a lot just cleaner. Okay? So, I don't know, take your pick. Let's do it that way. So I'm going to do it the second way. I'm going to put the origin there. And we'll call this X and Y. All right, so then we got our typical layer, typical pancake of chocolate milk. And we got to get that thing out. And so what do we want? We want the little bit of work to move that one layer. Okay? So what's the little bit of work to move that layer? It's going to be force times distance. And the force is going to be the weight. So this mass density times g, that's the weight density, times volume. That's the force. And then the distance it's going to go is how far is it going to go? It's going to go this distance right here. And so what is that distance? Well, so here is our y-coordinate, like that. Our y-coordinate is from the vertex of the cone up to the layer. And then the whole thing is 6 meters tall, so what is that distance?
6 minus y.
They want 6 minus y. You agree with that?
Yeah.
6 minus y. Okay, so, and then we got the rho there is 10, gamma is 1060. And then times g will give us the weight density in newtons per meter cubed. So that's that. So what's left is the volume of that little pancake of milk. Okay, so what's the volume of that? The volume of that is pi r squared d delta y. But then the radius is a function of y. So we need a linear relationship that gives us the radius at any height y above the vertex. So we know that when the value of y is 0, so make a little table, value of y is 0, radius is 0, value of y is 6, radius is 3, so that's an easy relationship. R equals, so you don't, so if you just can, 1/2 y, it's just going to be 1/2 y, right? It's just going to be 1/2 y. So on these easy ones, hopefully you don't have to like set up the whole point slope form and plug things in. And you can just see that r is always 1/2 of y. Okay, so then we got the volume is pi times r squared, 1/2 y, quantity squared, delta y. And that's our volume of the typical layer of chocolate milk. It goes there. And so then we want to take all the, so that's the setup. So then the total work is what? Sum of all the little bits of work. Important principle right here, right? Because you're going to get a different context. You're going to get a different context. It could be some other kind of physical thing. But this is the principle that applies, that if you want to get a total amount of something, you're going to sum up all the little amounts of that thing. All the little amounts of that thing, right? Total work is the sum of little amounts of work. Total force is sum of little amounts of force. Total mass is the sum of little amounts of mass. Okay, so then we're going to do 1060. Can I fit here? Probably not. 1060 times 9.8 times pi, not even close, pi times 1/2, and 3 lines probably, 1/2 y squared, times 6 minus y, dy. Those are all multiplied together. So mass density, newtons per meters cubed, times the volume gives newtons, times distance in meters, newton meters. So all that is our newtons, and then that's 6 minus y. That's not 6 minus y. It's hopeless. There. Okay. Questions on that one? Oh, then from what to what? 0 to 6. Okay, like I said, if you orient the axes here at the top, and then say a positive down, and then x to the right, so what's the trade-off? The trade-off is, this is easier, because then this is just y, and the distance that it has to go is just y. But then what's takes a little more work is then that radius as a function of y is not real simple like this. What's that? Oh, it's not filled all the way? Okay, thank you. So mine is filled from 3 to 6. Oh, filled with 3 meters. Filled with 3 meters. Okay, so y has to go from 0 to 3 then. Thank you. Because it's going to be, so y is 0 down here. It's going to be the first 3 meters of layers there. Okay. What? Is that not right? Because I'm orienting y here. Y is 0 here, and positive y goes up this way, right? So if it's filled up to 3, then that's this. This is what's filled up. And my y 0 is here, and y equals 6 is up here. Do you see? Other questions about this one?
Yeah.
Please.
Because, wait, you don't have, it says to empty it out over the top, you don't have to take it all the way to the top.
I did. My distance is 6 minus y. That's that. But which layers am I taking out? Y equals 0 all the way to y equals 3.
Gotcha.
So, yeah, but I did take it all the way out to the top. That's right, 6 minus y. Other questions? Yeah?
So say you were taking it to a valve that's 5 meters up.
Okay.
Would it be
So
5?
taking it out, so there's a hole right here.
Yeah. Would it be 5 minus?
So
5?
then now your distance would be to there. The distance I need to move it would be from there to there. And that would be 5. That would be 5 meters above. So it'd be 5 minus y. Okay, which makes sense because it's all just going 1 meter less, right?
Yeah.
So 1 meter less than 6 minus y is 5 minus y. Yeah. Other questions? Yeah.
On a test, once we have the integral, can we just calculate that with our calculator, or do you want
So I may ask you to show the integral work by hand. Okay? So that might incorporate some of the techniques we learned in the first part of the course. I would never give you really difficult like that, but it's possible that you had to use some of the basic techniques we learned on the first test. Not crazy hard, but you gotta use some of those. Now, setting up the integral would be worth a majority of the points, but for full credit, showing that you still know how to integrate by hand on the basic techniques that we learned. Other questions on this one? Okay, let's do a couple of these book problems. Let's see. So, perfect. Look at that space. Okay, so number 30. So if you didn't watch the video, I did make an error, and I corrected it on a video at the end of class. Well, then at the very end, I made another error with the limits. I did 3 to 6. It should have been 3 to 9. But that was a less significant error. But anyway, so except for that, the video is correct now in terms of the gasoline truck. Okay, so this one, is it filled? We got a milk truck, horizontal cylindrical tank, diameter 6 feet. When it's full and when it's half full. Okay. So we got the truck. 30. And it's all full, and the diameter is 6 feet. That means the radius is 3 feet. And now we're doing hydrostatic pressure. So for this one, again, it's a trade-off. So you can put your origin at the center, and then this equation of your circle is easier, but then the distance to the top surface is a little more work. Or you could put your origin at the top, then the distance to the surface is easier, but your circle is slightly harder. So I think I'll do the second way again. I'm going to do it this way. And then for the next one, we'll put the center of the circle. Okay, so for this one, let's do it this way. And then for the next one, we'll do it the other way. So let's do coordinate system like that. So I'm going to make positive y going down and x like this. And we got a typical slice. Okay, so does it matter how long the milk truck cylinder is for hydrostatic pressure? No, pressure is only a function of depth, right? So if you have a swimming pool that's 5 feet wide, the pressure profile going down is the same as a swimming pool that's 100 feet wide. Pressure is only a function of depth. It doesn't matter how much lateral water you have next to it. What matters is how much water you have above. Okay? So if the pool is 100 feet or 5 feet wide, still, as you go down, it's the same pressure profile. Okay? Yeah?
I was confused on how you made y positive rather than negative. Because it's going down.
Yes. But we're in control of the mathematics. So I'm going to make positive y going down. That's just so you're just yeah, so you're just used to it. You're just used to y being up and x being to the right. But it doesn't mean we can't make y down. It makes it easier for us. What? Hello? Yeah, and I could make this x, and I could make this positive y. You're just so used to the conventions that you just thought that was the way the universe is. This is valid too. So now you're really learning something.
Is there any benefit?
What's that?
Is there any benefit?
To making y go down positive?
No, you're not.
No, this is no. Except that it's a good conversation. Yeah, so it's so that you, like I said, now we're actually learning something rather than things are always one way, right? Things are always one way. So we'll go back to this.
But if you did choose to make the origin in the middle of
Yeah.
the circles and integrated with those like limits, it would still be used except
No, we're going to have different limits
Right.
from this.
But I'm saying even if the interval is slightly different, if the limits are
Yeah, no, so that's right. There are more than one. Like I said, there's another way to do this. We could put the origin in the middle. You get an easier circle, but then your depth expression is a little trickier. Here, the depth is really easy because the depth equals y. But then your circle is slightly, just have an adjustment on the circle equation. So let's do that circle equation. What is the circle equation? This is the point then 0, positive 3, okay? And so the equation of the circle then is x minus 0 squared plus y minus 3 squared equals radius squared, 9. Okay, so there's our equation of the circle. And we know that if we want the total pressure, total force is going to be, how are we going to find the total force? Sum up lots of little bits of force. Sum up lots of little bits of force. That's how we're going to get the total force. And every little bit of force is going to be pressure times area. Right, pressure times area. The pressure is the, what do we got here? 64.6 pounds per foot cubed. Okay, so the pressure is going to be, it's going to be that weight density times depth. And then the area is going to be length times width, or width times height in this case. Okay, so it's going to be the 64.6. What's our depth? What is the depth of this below the top surface of the milk? Y. And that was courtesy of putting our origin there, right? So the depth is the same as the y coordinate, okay? And then the width of this thing is 2x, right? From here to here is 2x. And the height? Delta y. So there's the area of our little rectangle. So this is the basic setup. All we have left to do is get x in terms of y. And that you just solve this for x. Square root of 9 minus y minus 3 squared delta y. And that's our little bit of force on that typical horizontal strip on the end of the milk truck. So then the total force is sum from what to what? 0 to 6. 0 is the top layer, 6 is the bottom layer. Now, one disadvantage to choosing the way we chose the origin here was now for solving the integral, you would need to do a substitution. But then, yeah, the other way then you wouldn't have to do that initial substitution. But so here you would do a substitution like u equals y minus 3. And then you would end up getting two integrals because then y would be u plus 3. And then you distribute the u and the 3, and then you'd have kind of two integrals to do. One would be undoing the chain rule. The other would be table integral. But we'll just stick with this for now. Okay, questions on total force on the side of the milk truck. Agree? Follow it?
If you did it at the origin.
Yeah.
With your.
So this would be x squared plus y squared equals 9.
And then the y-axis would just be 3 minus y.
Yeah, the depth would be kind of funky. So if we did it this way, I'll do it in blue, okay? Then the distance, the depth that we have to, this is your depth. And this is your y coordinate. So it'd be actually it'd be y plus 3. The depth would be y plus 3. To get this number here, you'd have to do y plus 3. You see it? In this case, for the way making positive y down like that. And then you'd have to integrate from -3 to 3. Did you ask that? Who asked that question? Yeah. So then you'd be integrating from -3 to 3, and your depth would be y plus 3.
So since we're measuring out the depth, we should make a positive y down usually, make it easier.
Yeah, I think this is making it easier.
Even if you put like the origin in the middle of the circle.
Yeah.
it's still okay.
Yeah, I think that's easier to see that the depth now is y plus 3 rather than having it be a subtract. Like if you had y going up, you'd have a subtraction
Right.
that might be a little trickier to see. But I think making positive y down is helpful here in both ways. Both ways. Okay, other questions on this one? All right, and do the gate, and we'll be done.
So that's for half that, would we just do the -1 from 0 to 3?
Oh yeah, so then I forgot. So half that, the way we had it. No, it'd be from 3 to 6.
Oh,
Right? Because I put the origin up at the top, right? So then the first layer has a depth of 3, a y value of 3, and the last one is 6. So yeah. So part 2 for that would have been the same integral from 3 to 6. Yeah.
If we did it from the origin, would it have been 0 to -3 or 0 to 3?
Part B
Yeah.
depends where you put your y-axis up or down. So, but you're saying you already did it, right?
Yeah.
And you definitely didn't put your y-axis positive down. After you couldn't have possibly put your y-axis positive down.
I don't know what's up and down anymore.
Okay, but you were so surprised that could possibly be the case that you had to have done this. So then you would do from -3 to 0. Yeah. If you put your origin here and positive y up, then you would be doing from -3 to 0. Yeah. Okay, last one. The pressure on the door. So this is 2 meters, and then this is 12 meters, and there's this little door with a 4-meter diameter. Then it's filled up to that line there, and so then this is all okay. So that's all filled, including that. And so we're asking, what is the pressure on that gate down there? So I'm gonna put the origin on this one. I'm gonna put the origin at the center of the circle. Okay, and I'm gonna make positive y go up. So I'm going to make it like a standard coordinate system this time. Okay. So what do we got? We got our standard slice. this, and we want the pressure on that. Again, total force is going to be, how am I going to get the total force? Oh, thank you, finally learned it. Sum of little bits of force. It's not trivial. It is not trivial. When you come to the test, you're going to have you're going to have something different that we've never seen before in terms of the context, the quantity that you're doing, and you've got to apply this correctly. All right, so then, so the total force is going to be pressure times area. We're doing red for the setup work. A little bit of work, no, force. Pressure times area. Okay, pressure is going to be the weight density. And is it water? So it's going to be, what, 1,000 times 9.8? That's going to be our weight density times the depth. That's going to be the pressure. And then the area is going to be, again, width times height of this little strip. Okay, and we need the equation of that circle, which is easy by the way that I've set this up now. The equation of that circle is x squared plus y squared equals 2 squared or 4, so it'd be 2 squared. Okay, what's the width? The width again is 2x now. Let's do one thing at a time. So 1,000 times 9.8. Okay, should we do the depth now? So the depth is from here to here. So it's from the top surface of the water to the typical strip. That's the depth. Some people are saying 10 minus y. So let's see. From here to here is our y coordinate. That little piece right there. From the origin up is y. And then from the origin all the way up to here is 10. This is 10. So I think I agree with 10 minus y. Yeah, that's awful. That's right. Everyone see how that's 10 minus y? It's y up from the bottom of the tank to our strip, and it's 10 all the way up to the top. So we need from the strip up to the top, which would be 10 minus y. Okay, width is 2x again, right? It's that whole thing from there to there, 2x. Height, delta y. And we'll just plug that in the next step here. So it's going to be the integral from, so all our layers go from what to what? 0 to 2. 0 here to y equals 2 at the top. 9,800, 10 minus y, 2, okay, what's x? Radical 4 minus y squared, dy. Questions?
This give me another like double integral one.
Yeah, so this is what I was talking about before, but it's easier to see now. So you're going to have to make this into 2. So the 10 will distribute to all these terms, and then you have a table integral, okay? 9,800 times 10 times 2 times this radical, you could do that from the tables. All right, then you have the minus y distributed. So it would be 9,800 times minus y times 2 times this square root. How would we do that? Undoing chain rule. Why? Because you have this minus y is exactly a factor of this derivative inside here. So here's your composite function, and you have its derivative out here. Undo the chain rule for that when you multiply this by y. Yes, sir?
So I was looking online at this one to set another example.
Yeah,
And they had the same integral, except they went from 4 to 12. And
Then they must have put the origin up here and then gone down like this from 4 to 12.
I think that, is it possible to remove that gate, like they're bringing it out of the water? To me, it seems like that's what they're doing.
Well, it's got to be a difference. First of all, it's got to be a difference of 2, not 4 to 12.
Yeah, I don't know if
That doesn't make sense.
everything else is right. So you just got.
I don't see how it could be 4 to 12 because the distance, one radius is 2. So I don't see how you would have a distance of 8 from 4 to 12 when you're only going across a radius of 2 there in terms of your adding up your strips. Other questions? Yes, sir?
Can you just explain how you get the 2x?
Yeah, so our x-coordinate is from here this way. So like from here to here is the x-coordinate. From here to this point, that right there is x. So this goes back to all the volume integrals we did. Seeing coordinates. So therefore, if from here to here is x, then this is twice x. So this is like negative x to x. That's twice x. Other questions? Okay, good. I'm satisfied with my part in helping you get ready for this exam and this part. Okay, I think we did good today. So now it's up to you. Now it's up to you. Any last chance for questions? Okay. So we're going to go on to new stuff, which will not be on the exam, but you'll have homework for it Monday. For Monday, okay?
Do we do homework in the next class?
No, study for the test. Study. So just in case you didn't notice, so I just reposted the study for exam. Here's good practice problems, but they won't be collected. So from the book, and then I posted this review outline. There's nothing on the exam that's not mentioned here or something we emphasized in class. Okay, everything on the exam comes from this list of things. So make sure that if you want to succeed, you've got to cover all these bases, and then you will succeed. Question?
Will the answer still resolve the
No, but I tried to pick as many odds as I could, because all the odds you have the answers in the back. In terms of the evens, if you want to catch me in office hours, or if there's 1 or 2, you want to email me, I could get you answers. Yeah.
could you have longer office hours tomorrow?
Ask my wife. I got to get home and help. She makes dinner, and the kids are crazy. So, when are you thinking?
I was thinking maybe like a little bit like past 4.
I'm 3 to 4:30.
Like past 4:30.
Yes, so 4:45. I could do 4:45. But I got to be home at 5.
What about in the morning?
What about in the morning?
Do you have another Calc 2 class we could sit in?
No, I don't. But the videos, I mean, that's the same thing, right? The videos are there. That's like another class. So, yeah, 3 to 4:30 tomorrow, or by email. If 3 to 4:30 absolutely doesn't work for you, then email me. We'll try to set something up. We'll try to figure out a time that works for both of us. Okay. Other questions? Okay, let's press on. What? Is Calc 3 easy?
Easier.
No, not if it's taught. It's no. This is new stuff. You'll have homework for this for Monday. Okay, now for something completely different. Oh, did someone bring these for me?
Yes, that was.
That was the teacher before. She left them there. She's like,
Oh, I thought someone was like the volume problems of Kisses so much that they brought me Hershey's Kisses, right? Because we did volumes of Kisses.
I did ready for the test.
What's that?
Actually, they're cross
Okay, so what is a sequence? A sequence is an ordered list of numbers. So the key to a sequence, it's a list. It's a list. Okay, a series. So if there were just one thing you learned out of this whole chapter, it would be this. But we're going to learn a lot more. But a series is the sum of the numbers of a sequence. That's the key, and you have to keep that in mind. We're going to get into down in the trenches of numbers everywhere and procedures and trying to memorize the rules and all these things. But if you lose sight of this, then there'll be no hope. There'll be no hope to make sense of what we're doing. Okay, the sequence is the list. First number, second number, third number, and then the series is when you sum up all the numbers in that list. In that sequence. Okay, so tonight we're just going to talk about sequences. And then the rest of the chapter is on series. Okay, so A sub n. So often sequences look like this. So A sub n is the nth term in the sequence. So that's the okay. So another way to put that is A1, A2, A3, . So that means the same thing, right? So the first A1 is the first number in the list. A2, the second number in the list or the sequence. Okay, so for example. One, 3, 5, 7, 9. Okay, and so this is so when you just leave it with the ellipses like there, dot, 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 that means it's an infinite sequence. This just keeps going on forever. Okay, so what is A3? 5. A3 is 5. Okay, what is A6? What is A6? 11. Okay. So what do we say? A3 equals 5. A6, B6. Equals 11. Okay. So find a formula that is an expression of n that gives A sub n. So find a formula So the question is, what is this expression with n's such that if you wanted to know what, say, A236 was, you could get it quickly because you'd have this expression. You just plug 236 into your little formula, and it would tell you what A236 was. Okay, so if some of you have seen it already in this particular case, but if you don't see it quickly right away, what helps is to make a table of values. So do n and then an and make a table, and then it helps you to see the pattern. So this is like 1, 2, 3, 4, and then was this 1, 3, 5, 7, and then maybe higher numbers are more helpful. So let's go up to say 7. 5 is 9, 11, 13. So 7, comma 13. 8, comma 15. This is what these bigger numbers are what helps to see what the formula would be. 9, comma 17. So what are we doing to n to get a sub n? As you're seeing it. So you see that 7 times 2 is 14. 8 times 2 is 16. 9 times 2 is 18. It's always one less than 2 times n. So how do we express that? 1 less than 2 times n. 2n minus 1. If you can't see it right away, again, making this table is helpful to look for patterns. Okay, make a table like this to look for patterns. Okay, so let's see. Other sequences. So a sub n, I do that fast enough, all right? A sub n equals n plus 1 over n. Okay. C sub n equals, these are just examples, negative 1 to the n, 2n plus 1 over n squared. So what I want you to do is, I want you to write out the first 4 terms of each sequence. What are the first, so let's just call this B. I already read A, just leave it there, it's fine. So figure out what the first 4 terms of each sequence are. Okay, first one, did you get the first one? 2, right? 3 halves? 4 thirds? 5 fourths? Dot, dot, dot. Okay, this one? Negative 3 is the first one? Then? 5 fourths? Negative 7 ninths? Positive 9 sixteenths. Okay, that's called an alternating sequence. Alternating sequence, because why? The sign alternates. Negative, positive, negative, positive. So that's called an alternating sequence. Okay, questions so far? Okay, so for these, so I'll just leave those up there. Those are the ones we just did. Okay. Okay, a sequence is convergent if the limit as n approaches infinity of a n exists. So what are we saying? It has to get, the list, those terms, as you go further and further, it has to keep getting closer and closer and as close as you want to a certain number. That's what the limit means. That you pick how close you want to get, and eventually you'd get that close, and then you'd get closer after that. So you can pick as close as you want to the limit, and go up far enough in the sequence, and you would get within between that number and the limit. Okay, and then you'd get even closer. Okay, that's what the limit exists means. Okay, otherwise, it's called divergent. Okay, so let's go back to the ones we looked at here. What about 2n minus 1? 2n minus 1. Convergent sequence or divergent? 2n minus 1. Do that list of numbers converge in on a particular number and then get as close as you would ever want to that number? No. What this just gets bigger and bigger. That's divergent. It just gets as big as you want. So that's not convergent. All right, what about this one? 2, 3/2, 4/3, 5/4. So you look at n plus 1 over n and think about really big values of n. Does that start honing in on a particular value, converging onto a value? Which would be 1. So an is convergent and its limit is 1. What about this one? -3, 5/4, -7/9, 9/16. So let's look at what's happening here. So the numerator is 2n plus 1, and the denominator is n squared. And it alternates, yes. But what will happen for really, 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 really big values of n? The denominator is just going to take off compared to the numerator. And the denominator will get huge compared to the numerator, n squared compared to 2n minus 1. Therefore, it's going to converge on 0. It's just going to do it by hopping back and forth around 0, right? So every time it hops over 0, it gets closer to 0. And just keeps hopping back and forth and getting closer and closer in on 0. So these two are both convergent. This one's convergent to 1. This one's convergent to 0, but this one is divergent. Another type of divergent sequence is like this. So not that it necessarily gets infinitely big, but it doesn't converge. So like tangent of so what's tangent? Tangent is the slope of the terminal side of your angle. So what's happening in here is we get 2n minus 1. We're going to get 1 pi over 4. Then, so this is our 1, 3, 5, 7, right? So we're going to get 1 pi over 4. It's here. 3 pi over 4 is here. Then 5 pi over 4. 7 pi over 4. 9 pi over 4. So what's happening here? What are the slopes of these lines? At pi over 4. Angle pi over 4. Angle of 3 pi over 4. Splitting these quadrants in 2. Slope of that line is 1. Slope of that line is -1. Then 1. -1. So this is just going to march up the odds. This is this one right here. Times pi over 4, which is going to give us these slopes as you're just going around and around forever. Okay? So it's going to be 1, -1. 1, -1. So there's other ways to get alternating sequences besides just the -1 to the n. So this is what made this sequence alternate, but there's other ways to do it. Like you could use a trig function. correctly, and that will make it alternate. Convergent or divergent? Does not get close to a number, so therefore divergent. That limit doesn't exist. You keep bouncing back and forth between 1 and -1. The limit doesn't exist. You don't hone in, converge upon a single value, okay? So that's divergent.
Can you have like a to the negative,
What's that?
like a to the -1?
A to the -1.
Can n ever be negative in the series? Or the sequence?
Oh no, right. So n will always be as a list. It's an ordered list. So this will be the first one in the list. So you never have a negative value in the list. Like, does that make sense? Like, that's the first number of the list, second number of the list, third number of the list, fourth number of the list. So every list will be like that. You'll never have a negative member of the list. It'll always start with the first, second, third, fourth. So n is which number it is in the list, first, second, third, fourth. Okay, so sequences are similar to functions. Okay, so let's talk about that. Questions on convergent versus divergent? Okay, comparing sequences to functions. So for instance, a sub n equals 1 over n squared. So what function is that kind of like? What function, if we were to write a function f of x, 1 over x squared, right? So the n is like kind of like the input, right? And 1 over n squared is like the output. So what's the same about these? So there's similarities and differences. So what's the same about these? Well, is this a convergent sequence or divergent? 1 over n squared. Converges to? Yeah, so the limit as n goes to infinity of 1 over n squared equals 0. And what's the limit as x goes to infinity of this function? So it's the same thing is happening, right? So x is getting greater and we're taking 1 over x squared. N is getting greater and we're taking 1 over n squared. So it's going to be the same limit. So this is helpful because if we're analyzing sequences in terms of we're analyzing them in terms of limits to see if they converge or not and what they converge to, then we can use just our knowledge of limits of functions to do that, right? Because we can just turn it into a function and evaluate the limit of the function. And you guys have learned some of that in Calc 1. Okay. So that's the main thing, how they're the same. So different would be if we were to, say, sketch. If we were to sketch these. So what would a graph of the sequence look like? And what would a graph of the function look like? Yeah, the continuous function, right? 1 over x squared looks like this. Also, x is valid as negative. So when it's negative, it's the mirror image over the y-axis. So now what does the graph of 1 over n squared look like? Yeah, and what would the first point be?
Whatever your first n value was.
And what is the first n value? Yeah, so 1. So the ordered pair would be 1, 1. Okay, smartass. make the x go this way. Okay? So, first one is 1, 1. And then the next one would be 2, 1/4. And then the next one would be 3, 1/9. So it would just be a bunch of points. But the limit of those points, or where they're going, is the same. Okay? So this is what? We know this limit. That function gets infinitely close to 0. And these points do the same thing, right? So the limit in the end is going to be 0. So this is 1, 1. 2, 1/4. 3, 1/9. Okay, and if we did it conventionally, those points would land right on this, right? Those points would land right on the function. And so the limit would have to be the same of the function and the sequence. Okay? Okay, questions on that? So again, why is this helpful? If we're analyzing sequences to see if they have they're convergent and what they converge to, sometimes it's helpful just to think about the equivalent function, because whatever the function does for large input values of x is what this sequence does for large value of n. Okay. Yep. So now some common forms of sequences. Okay, first common, let's see, 1 over n to the r. One over n to the r converges if, so n is that's our counter, converges if r is greater than 0. All we need is a positive exponent on r, and if you make n big enough, this will eventually get as close as you want to 0. So what are we saying? We're saying the limit as n approaches infinity of 1 over n to the r equals 0 if r is greater than 0. Okay, let's see that. So we can use the equivalent function, y divided by, say, x to the, all right, I'm going to call it a, okay? So let a go from -3 to 3, and we'll do other steps. So certainly if, we'll start with a equals 1. Certainly if a equals 1, or in this case if r equals 1, we got 1 over n. 1 over n clearly will go to 0 for large values of n, right? So that's what I'm showing here. Okay? If you make that r bigger, then it'll just get there faster, right? So I'm making r bigger. When I make r bigger, it just gets to 0 faster. So what about between 0 and 1? So here's 0.96. Here is negative 0.54. I didn't mean to go that far. Well, I need what do I need? Let's do negative 1 to 1. So for values between 0 and values of r between 0 and 1. Here's 0.56. It makes it, it just gets there slower. Here's 0.18. Okay? So notice it's hovering really high for a long time. So it's going to just take a lot longer to get to 0. But we never run out of numbers, right? We never run out of values, x values or n values. So we'll get there eventually. What about when it is equal to 0? Then what do we get? We just have 1, right? So just pretend that's 0. At 0, it'll just be the line 1. So that will not that converges to 1. Okay? So that converges to 1. But it's trivial because every single term of the sequence would be 1. Then if it turns negative, then we got increasing sequence. Okay? So this, what am I showing? I'm showing you that as long as that a value or r value is greater than 0, it will make it, so here's 0.04. All right, it's just going to take a long time to get there, but let's do it. So we'll zoom out on the x-axis. Okay, 2,600, 5,000. This is 50,000, 24,000. Now we're in the millions here, and we haven't even gotten to 1/2 yet. Okay. But we'll never run out of numbers, right? We'll never run out of values. So let's just go out here and plot a point. So when you're at 2.57 billion, you've made it down to 0.4. Okay? But like I said, so a billion is a drop in the bucket compared. We'll never run out because it's an infinite sequence. So you just got to make x big enough, and then you'll finally get close to 0. Okay? Where are we at? Okay, so that was that was number 1. So number 2, another form is p to the n. And now notice, so now your n is the exponent, p to the n. So the limit as n goes to infinity of p to the n that equals 0 as long as p is, what would you multiply together over and over and over again, right? So every time you advance n by 1, you multiply by this number p again. This is what this is saying. So what numbers multiplied together over and over and over again will eventually get you to 0? Fractions, right, a number between 0 and 1, right? So actually anything from -1 to 1, keep multiplying it together over and over again. So like 1/2 times 1/2 times 1/2 times 1/2. Every time you multiply it by 1/2 again, you get closer to 0. Or 7/8 or 1/8, whatever. Okay, this also equals 1 if p equals 1, but that's trivial. And they're just all 1s. You just have a sequence of 1s. 1, 1, 1, 1, 1. But if this p is greater than 1 or less than or equal to -1, it's divergent. Which makes sense. If it was, if it was 2, it'd be 2, 4, 8, 16, 32 would be your sequence. And that wouldn't converge. And if it's negative, then it's going to alternate and get bigger. So that's that one. So let's write them both down at the same time. 1 over the r goes to 0. If r is greater than 0. So these are 2 common forms that you see. Okay, so practice. Do they converge or not? And if they converge, what do they converge to? So we're applying different things. We're applying these 2 when these come up. We're applying the idea of a function, making it into a function, and seeing what we can do to find the limit. And then common sense, okay? So there's lots of things going on here. One over 5 to the n. N squared minus 1. Sometimes you just start writing. If you're not sure, you can just write out the first 5 terms and see what you can deduce. So they're not one size fits all. You do different things on different. Sometimes they require a little algebra first. Okay, so see what you can make out of these in a couple minutes. So convergent or divergent, if convergent to what? I'll take attendance. No. Yeah.
Not hear you call my name.
Gotcha.
Thank you.
So the first one is like 1/5 to the n, so that's convergent because that's p less than 1. Got it? How about this one? So for this one, we could think about changing it into a function and then just applying pre-calculus to do the limit, right? So what's going to happen when x gets really, really big? Do you remember from your pre-calculus here? Yeah, so you take the ratio of the leading terms, right? So the top will be like, for big X, will be like x squared, and the bottom will be like x squared. So really this goes to 1 over, you look at the coefficients, 1 and 1. So 1 over 1. Okay, that's because these are the same. That's because these degrees are the same. Right? If this was bigger down here, it's going to go to 0. And if this is bigger up here, it's not going to converge. It's going to be divergent to infinity. But if they have the same, then it's the ratio of the coefficients. 1 over 1. How about this one? Divergent. It's going to get really big. How about this one?
I was wondering if it's a conversion and one. Never mind.
This one? No, this is going to get huge. Right? This is going to get way big compared to that. This is divergent because the limit doesn't exist. And this one? This is the same as pi over 3 to the n. P is greater than 1. That's a little bit greater than 1. Divergent.
Could you also say like pi is greater than 3, like the base?
Yeah, but this is stronger, right? This is applying what we talked about, right? This is the same as pi over 3 to the n, where that's greater than 1. So it's divergent. Anybody want a Hershey's Kiss?
I'll take it.
I already had my chocolate for tonight. Anybody else?
Let's say injected it.
I'll take
Anybody else? Unless they injected it. You want another one, Chris?
I got 30 minutes to drive. So.
Hey guys, study. See you Wednesday. Study hard.
It's like a little meal plan with you guys. See that? You guys have my number, man? On campus.